All right, so let's go ahead and get started on our Pset 2 solutions. So I'm rolling a 20-sided die in a long-running D&D game that has 15 rounds. So what are the number of possibilities if I have 15 rounds and I'm rolling that 20-sided die that can occur? Well, let's go ahead and set up our R over here. And so if I have 20-sided die each time for 15 rounds, I can get 20 potential outcomes. So if I want to look at the total number of possibilities, I'm going to do 20 to the 15, and that's a large number right there. But that's it. Excellent. All right. That's all there is to it for number one. Actually, let's go ahead and let's set up our little notebook. So number one, solutions. Let's look at number two. I have a difficult time selecting my clothes in the morning. I believe that I have a million outfit possibilities. I have 2 options of socks, 5 types of shoes, 10 shirts, 7 pants, 3 belts. Is my claim true? Do I have a million possibilities? Well, let's take a peek. So I have 2 options. That's one possibility. I could pick 2 of those. I could have 5 types of shoes. I can do 10 shirts. I can do 7 pants. Again, this is just going from our possibilities that we kind of defined in lecture 2, right? So we're looking at the ways of selecting that, and you can kind of multiply those together to get the possibilities. And it's not, I don't have as many options as possible as it appears here. So that's number 2. Number 3, the problem of what are the possible permutations for my outfit? What about the combinations? Well, one way that you can deal with this is, let's just say, for one way that we can solve this is, basically we need to define effectively what is our total number of distinct objects and what are we selecting from, right? So our total number of n is, I can just say, well, I have, for example, let's do permutations first. So I can do permutations, and my n will be, let's say I have 2 plus 5 plus 10 plus 7, 10 plus 7 plus 3. So I can say, those are my total options, and I can pick for my outfit, for example. So that is my n. And let's say I can pick, what do I have to pick? I have to pick basically what would count for a sock, or basically, I can imagine I can actually pick anything. But let's just say I'm defined where I have to pick a sock, a shoe, a shirt, a pant, a belt. So like 5 items of clothing. So I can make it easy and just say I can pick any 5 items. So I could have an outfit where I just have 2 socks, a belt, or what, just to make it kind of straightforward. So I could have this solution, and then the same thing for permutation, or except for combinations, would just be to switch here. So that could be my solution effectively for this here. So that is one potential outcome that can occur. I can do it a little bit, better per se. And instead, let's say, for example, I want to look at the permutations, and I have, okay, so let's just break it into pieces. So I have 2 options for socks, and I'm going to pick one of them. And then I would do multiply permutations of, let's say I have 5 shoes, so I have 5, I'm going to select 1 pair of shoes, times, and you get the picture. Permutations, actually, let's go ahead and, let's go put the multiply here. Let's do permutations, let's see, hopefully that will work. I have 7 pants, I have to select one of those, times permutations of, I have 3 belts, I have to choose one of those. So I can do this. So I can look at this as a possibility, and I could just combine the same thing with, we can do combinations. Combinations. And I'm just going to Control C, boom, 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 and then enter. And you can actually see, unfortunately, the same result effectively there. So multiple ways you can kind of probe essentially the scope of that problem. So that is something to think about and consider. This problem has a little bit of an open end to it, but again, you can just simply multiply those in order to get the total number of those permutations. All right, let's move on to number 4. So let's go back to the 20-sided die. What is the probability that we roll a 4 or an even number? So again, we want to go back and we want to examine effectively our notes and which equations that we are going to want to utilize in these problems. So specifically here, we're looking at an event. So what's the probability of rolling? And it's an or statement. So we have to look at, is this a mutually exclusive or is this not a mutually exclusive event? So if it's mutually exclusive, we should remember, so if it's mutually exclusive, we have this following expression. So we have probability of A1, and then union with A2, looks like A3, blah, 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 blah. And then we will just simply add those individual probabilities together. If they are not mutually exclusive, we have to take probability of A and B. It's going to be equal to probability of A plus probability of B plus probability that A and B are satisfied simultaneously. So let's go look back at that. So let's look at our problem here. So we are asked, what is the probability that we roll a 4 or an even number on a 20-sided die? Well, again, mutually exclusive events, basically we can't have one condition satisfy two, basically outcomes. So outcome A is we roll a 4, outcome B is an even number, so those are not mutually exclusive events. So what we're going to have to do here is actually solve this. So let's go ahead and let's pull up our R, and let's go a little bit over here. So what is the probability that we roll a 4? Probability A. And again, oftentimes, so I'm going to have A be a 4, B is going to be an even. So what is the probability here that we roll a 4? So for a 20-sided die, oops, let's go ahead and bring this back up. So if I'm looking at a 20-sided die, that probability of rolling a 4 is going to be 1 divided by 20. The probability that I roll, basically, probability that I roll an even number is, on the other hand, going to be what? So I can roll a 1, a 2, a 3, a 4, so it's going to be a half. Then I'm going to subtract the probability that I roll an even number that is also 4. So that's going to be 1 divided by 20. And we've got that. So those are the mutually exclusive events here. So that's the probability I roll a 4 and it's even. So probability I roll a 4 and that it's even, well, a probability that, yeah, basically I get that. So excellent. So let's go on to the next problem. So the next problem is, what about the probability of rolling a 2 or a prime number? Well, these are also mutually exclusive events, and so 2 is going to be A, so the probability of rolling a 2 is 1 out of 20. The probability of rolling a prime number, so let's look and take a reminder. What are our prime numbers? So we have, our prime numbers are going to be 2, 3, 5, 7, 11, 13, 17, and 19. So we can roll 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 20 outcomes. So oops, not here. Let's go to our R plus 8 out of 20. So that's my probability of rolling a prime. And the probability that I roll a 2 and that's also a prime number is going to be 1 divided by 20. And there we go. So that's 4. Let's move on to number 5. So in the word Mathematica, if we're to pick a single letter, what is the probability that we select a T or a vowel? So again, these are mutually exclusive events. So probability of A is that we select a T, and probability B is that we select, or probability A2 is we select a vowel. So if we look at this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 letters. So how many vowels? We have, basically, if we pick, or let's do probability of T. We have how many T's? 1, 2. So the probability of A is going to be equal to 2 out of 10. Probability of B, we have A, so this is 1, 2, 3, 4. 4 out of 10. So we can add that up, and it's going to be 2 divided by 10, and then plus 4 divided by 10. And there we go, 0.6. Let's move on to number 6. Here we go. All right, let's get into problem number 6. So, what is the probability we select a diamond or black card from a deck of cards? So, are these mutually exclusive events? No, diamond is red, right? So, we can just add those together. We select a diamond or a black card from the deck. So, the probability that it's diamond, so let's do A is diamond, which is red. B is black card. So probability of A, that we have a diamond, is just a fourth. Probability of B is going to be equal to half. So we can go ahead, use our sophisticated R program to do this math. Just a joke, just a joke. And there you go. Yeah, let's look at number 7. All right, everyone, we are back, and we are about to get into our 7th problem that we have to have a little bit of a typo with. So we have 3 boxes. So box 1, box 2, box 3. And we have basically these number and different types of marbles in box 1, these numbers and marbles of box 2, these numbers and marbles of box 3. One marble is chosen at random, and assuming that there's no bias in selecting the box, so basically we're saying the probability of box 1 is equal to probability of box 2 is equal to probability of box 3, which is equal to a third. And given that we select a green marble, what is the probability it came from box 2? So given always, should kind of ring some alarm bells, given that we are going to be writing effectively a conditional probability. So if we remember, we're going to do probability of B sub 2, given that it is green. So probability that it came from box 2, given that it is green. And that's going to be, again, probability of, basically looking at here, probability of B2 green marble, green, over, let's zoom out here for a second, probability that it is green. So let's start to kind of tackle some of these, and let's be systematic in this problem. We're going to start getting to and define some variables here. So let's define, let's say, let's go here. Probability B1 set equal to a third. So let's control enter that. PB2 set equal to PB1. PB3 is equal to PB2. Additionally, we want to look at, I'm going to say tote B1. So the total number of marbles is, in box 1 is 8 plus 17 plus 24. Tote B2 is going to be equal to 8 plus 17 plus 24, 3 plus 12 plus 9, plus 12 plus 9. And then tote B3, we're going to say that that is going to be equal to 17 plus 5 plus 13. All right, so first thing, let's calculate the probability that it is green. So my probability of green is going to be equal to, so first of all, I need to add basically the probabilities of all of those 3 boxes. So they each have a third probability. So I first have a chance that I can pick any of those boxes. Then I need to multiply by the ratio of the green marbles. So in the first one, I have 24 divided by my tote B1. And I could do probability of, for example, PB1, just because we've already defined it, plus PB2 times, what are my green marbles there? 9 divided by tote B2, plus PB3 times, actually we'll go PB3 times, let's do the times here as well. PB3 times, how many green marbles do we have there? 13 divided by tote B3. So, and we can look at that, and you can see that value right here. Actually, let's not have that on that line. So actually, we may go back to here for the previous problem. Let's actually go back here for a little bit. Let's go over here, and let's put the combinations here, just so that we can see these here. Yeah, we need to define our functions. So yeah, now we can see those values. Oh, we were fine there, but we were not fine over here. So let's move this right over here, and we can do P green. Probability of green, and we can see that value right here. Excellent. So we can now, so that's a good start. So that's our probability of green. What is the probability box 2 and green? Well, that's going to be equal, or you can set that. So probability that I choose box 2 is a third. And then once I pick box 2, so that's an and, because again, probability that and that I grab that is going to be basically, again, that same ratio. So the box 2 is going to be, I believe, it will be the 9 divided by tote B2. So that would be probability B2 and green. So now I could do probability B2 and green divided by probability of green. And there you go. That's my value. It also asks us, what if we had selected basically a blue marble? So in that case, we would have to just switch up, really. We would have to switch these up. So let's go ahead and let's do this here, and then green and red. So probability that we are blue is, all I'm going to do is change. So there's 17 blue marbles there in the first batch. In the next batch there was 12. And then in the next batch, how many blue marbles did we have? We had 5. There we go. So we don't need to define that. Probability of 2 and blue. Probability 2 and blue. Probability of 2 and, unfortunately, BLUEE. So 1/3, and then again in the second one we have 12 blue. So we should be able to rock and roll now. Bang, bang, bang. Ooh, something's going on. So let's see what we got here. Let's see. Probability 2 in blue divided by probability of blue. Let's go. Let's take a peek. Let's take a peek at what's going on here. Because the problem in the second box we do have 12. So 1/3 divided by 12 total B. So let's see if we can, let's look at probability blue. So pretty low probability. Probability 1 times 17 over total that. There. Ah! Why is there... Oh, okay. My mistake here. Again, this is why we look at these. So we need to add this. That's a big mistake. There we go. It's always sometimes good to kind of double check your answers here. So let's go here. let's go here, let's go here, and let's go here. Excellent. And now we can go, what's the add here? Bang, 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 bang. Good. And we can do the same thing here. Good to catch that one. That plus sign was giving us some issues. And now let's do the probability that we are red. And the probability of red. And probably B2 and red. Probability red. Probability of 2 and red. And here we go. Let's go over here. Let's set this to the side a little bit. So for the first batch, how many red? We have 8. Second batch, second box, we are going to have 3. And for the last box, we are going to have 5. So this should be the lowest probability. So let's get this. We need to switch this from 9 to 3 now. And there we go. We got it. And we can look, and that kind of does make a little bit of sense that that should be the lowest probability, and it is, just by a smidge. Fantastic. So there we go. All right, let's go to the next problem. So we now have a question where if you take a mammogram for breast cancer, 8% will observe a false positive result. 90% of the people that have breast cancer will test positive on mammograms, and 1% of people over 50 have breast cancer. So what is the probability that a person has cancer if they have a positive mammogram result? So this is a problem where we're going to have to invoke Bayes' theorem. And the reason is that there are multiple possibilities that we have to effectively consider here. So, for example, we have, and we can actually deduce. So we have a given. So we always kind of want to start out with, for Bayes' theorem, probability of some outcome B sub R for A. So our A condition is what we're given. So we are given we're asked what the probability is the person has cancer if, so we're given that they have a positive mammogram result. So that is given, positive mammogram. So we are also presented with, we are interested in what is the probability the person has cancer, and the other outcome is not cancer. That's another possibility based on these kind of mammograms, because we could have test positive or false positive. So let's write out our expression. So in Bayes' theorem, we are going to look at probability of B sub 1 of A is going to be equal to probability of just B1 times probability of A given B1 divided by that same value of A given B1 plus probability of B2 times probability of A given B2. So we have those as our probabilities. So let's look at what is the probability that someone has cancer. Well, we're given that if we're looking at people above 50, that 9% of people has cancer, and 1% of people has cancer. So probability of this is 0.01. What is the probability of B2 that they do not have cancer? Well, that's going to be 0.99. What about the probability of AB1? So what is this saying? So given that they have cancer, what is the probability that they're going to test positive? So 90% of the people that have breast cancer will test positive. So that's going to be 0.9. What is the probability if I don't have cancer that I will test positive? And that's 8% basically. 8% will observe a false positive result. So that probability is given here. There you go. So let's calculate this out. So let's go ahead And let's go into R. Let's go to, this is number 8. So we're gonna say, let's get this all set up here and ready to roll. So we can just plug in these values. So I'm just gonna do this simply. 0.01 times 0.9 divided by, we'll put all these in here, divided by this, plus, we'll put that there, except now we got to switch it to probability. That's 0.99, and then 0.08, and then, yep, about 10% chance. Good. All right, one last question. Simulate a normal distribution. All right, so let's go back here. Let's expand us a little bit. So we need to simulate a normal distribution of temperature measurements. So our norm. Actually, let's go and I think we need to do library. Actually, we'll do it right here. So library tidyverse. Ooh, it's not popping up, so we need to do install.packages tidyverse. And then it's going to go in here. And let's do our norm. What was it? Our norm, I think. Our norm? Do we just need stats? But I think we'll get all of the good. We'll get all the good stuff. Again, this is the exciting part of sometimes working with R, but I think tidyverse will give us a lot of the critical critical functions. Take again. You know these are live videos. But again, the whole point is we're going to look at taking samples and we're going to see how, again, as we take more and more samples, we're going to better capture essentially that that population that we've worked on. So we did this in class, and hopefully this rings a little bit true. And by a little bit, I mean a lot true. So it's downloading all of the good stuff. But it'll be nice because then we won't have to do this again. So again, this is a really, really nice tool, again, that you can use for R for solving a lot of these problems. In the next problem set, you're going to probably see a lot of Mathematica because we're going to be looking at calculating confidence intervals based on some of the values. So, but it's just what we're looking at here. So you can see all the packages that it's kind of pulling out. Pull out stats too. You see the stop sign, it's basically saying it's still running, so don't, even though you're impatient and you want to finish your solution video and not have people look at all the different packages that are being uploaded and reflecting on how you should have done this ahead of time. Ignore those instincts and instead just wait and be patient, and then it'll get it done. Don't sing anything that is copyrighted. But you can see all the different packages that, again, tidyverse is a very nice one. So I would definitely suggest installing that package and utilizing it as well. ggplot too, that's a huge one. Google Sheets, if you're working with some of those. So there's lots of cool things that you can do in R. So it's a very nice, it is a very nice program. It's a very nice thing, tool to know how to utilize. And there we go. And I need to, again, read in the library. So read in the library. So let's see if we can pop it R norm. I think we need to sit it. R norm, here we go. So we need 8957 samples. We need a mean equals to 325, and we need an S standard deviation equal to 21. And I'm going to call this TDAT for temperature. So that's my TDAT. I can do mean of TDAT and we can look at those values. I can do SD of TDAT, and then we can look at that. Looks good. Makes sense from what we were trying to accomplish for the most part, especially because considering that standard deviation. So if I take, sample. So if I do sample of my TDAT, and if I do 1, 320 is not a good approximation of that. But if I do sample, and if I do TDAT 10, so if I do 10 samples, and I'm going to actually do pipe function. So pipe this to mean. So still not great. Actually, you could look at this again. So 335 is not good. 309 is not much better. So let's do sample of 30. That's looking better, right? 324. What if we do 50? 50 looks again, just different samples. Okay. What about 100? Oops. So 100, looking good. Again, we're getting closer to approximating essentially that sample. So the sample mean was 324. But again, you have a pretty large standard deviation here. What about 500? There you go. I mean, now you're starting to kind of see, and 1,000 will be pretty much on the money. So you can kind of see as we increase our sample size, we get close to that true approximation. So we can do one more run quickly. Bad, better, we're approaching it, and then you start to get really that consistent number. So more samples, more experiments, more work. We'll see you all next video. Thanks. Bye.